In this video, I'm going to be showing you the new functions I've added to my particle simulator to display this graph, just a typical graph, and also output data about collisions on the sides of the screen. I'm also going to be, as usual, linking my code in the description. So let's have a look. So I've imported this, don't know what it's called really, but I've imported this thing called Matplotlib. There it is. Also, as a sub set of data, I've imported pyplot and as PLT to make it easier to reference, because you can just write PLT instead of pyplot. Sorry, throat's a bit bad. All I've done here is I've used this code. This is my function to draw that graph. It's not really linked to any of my data yet. This is just a proof of concept really. Just thought I'd start off by drawing a graph and then I can work on filling in the data later. So just plt.plot. Plot just draws these points on axes. plt.xLabel gives a label to the x-axis. plt.ylabel does the same with the y. plt.title gives it a title obviously, and plt.show, obviously the most important part, shows this in its own screen. What else was it? Here we go. So I've changed a function down here to do the wall collisions. What it does is, every time, you must have seen this before, every time a particle hits the side of the screen, it will call this. This is new. And what this does is it appends the wall collision database. It does this for each side. So it can do it 4 different ways depending on which side is hit. It passes in these values: cont side, which is the container side, which side it hit, and the start time. So this will be basically the time at which that happens. It passes it back up here into this, the append wall collision database function. What it does is, impact time is time.time. What time.time does, it just gets the time at that precise moment. And then this is the buffer list. It stores labels, left, right, top, bottom, depending on the side. And what this bit does is it's a bit complicated, but it's quite clever, so just concentrate a bit. So for an in-range len buffer, so for the amount of times that is the length of this buffer, so 4 times, if the container side equals a value in the buffer, I'll just give my camera, something must have got it. If the container side, which has been passed in by the way, is a value in the buffer, so say if it was right, then the perpendicular speed is the speed which is stored in the original speed list. Okay, and the item in that list which represents the perpendicular speed is the ith item plus the integer version of n divided by 2.1. So you might be wondering what that means. Well, the thing is, I needed something to apply to any container side that could mathematically give me the correct perpendicular speed to put into the list. Now, if it's going left or right, then it will be going in the x-axis because x is along here. If it's going top or, well, if it's going up or down, it'll be in the y-axis like that. The thing is, any speed I value represents x values, and any speed I dot plus 1 value represents a y value. So what this is it takes n, which are on right now, so in this case will be right, and then it says, okay, so what's n divided by 2.1? Well, n here would be 1, because you got 0, 1, which would be about 0.4. And then, so you got 0.4 here. And then the integer of that, what is the integer version of 0.4? Oh, that's just 0. So speed I plus 0 is just speed I. So that represents a x value. Now this gets the x value of the speed from, well, it's just generic really, any x value. And it makes that equal to the perpendicular speed. And what this does then here, also, you know, if you add a speed, it just breaks to go onto this. Then what happens is it appends to the self-collision list the container side, so which side it was, left, right, top or bottom, the impact time, so what time it impacted, and this new thing we've worked out, the perpendicular speed, and that applies to all of them. Now if you check that mathematically, that will work for all values. 0 divided by 2.1, just 0. That works out to speed I, that's an x value. Right, we just did that one. Top, that's 2, so I plus int 2 divided by 2.1, that will be like 0.9 or 0.8 or something. That rounds up to 1, so speed I plus 1 is a y value. Same with bottom 3. N divided by 2.1 would be like 1.4, 1.3. The integer version of that, it rounds to 1, so speed I plus 1 is a y value again. Now that took me quite a lot of thinking, because it's not very simple. I had a bit of a light bulb moment when I thought of that. But yeah, that allows me to, well, it allows the program to check whether they should have x values appended or y values appended. And this is basically the database which stores information about all the collisions with the walls. And there is a button down here somewhere. I assume it's the last one, yeah. Button down here where if a click happens within these coordinates, then it will obviously, you know, draw a rectangle to give the effect of a click. That's not really important, and more importantly, it will print this list. It will print the collision list, and it will call the draw graph function to draw the graph as well. So yeah, that's that. I'll run it again. Just get some collisions in, and every time they collide, it will be registering the perpendicular speed, which side was hit, and at what time that side was hit. Hopefully in the future I'll be able to incorporate all that data into a series of graphs. And if I press this in a sec, it'll be quite a lot of data, but it will print out. If I press show collision database, here you go, squeeze text, and there's all the data. Yeah, I have to be careful that it doesn't get over capacity if I run it for too long, which might happen. I think I must have accidentally clicked off the graph page. Alright, so that's that. Thanks for watching.